So let's talk about sphere under the topic of mensuration. And first, we're going to discuss what is the volume of a sphere. And before we get into the details, let's try to understand what is a sphere. Everyone has experienced sphere in some format. Some of them are abstract as when we talk about our Earth, which is a whole sphere. If you see the India map here, there's a beautiful country of India over here, and we know the overall globe or the overall Earth is spherical in shape. But that's very abstract because it's very hard to see it unless you go into the space. But if you look at this object, which is nothing but a soccer ball or a football ball, uh, then you realize that it's a sphere. It's kind of a hollow sphere because it's hollow from inside, and it's a sphere in all shape. So basically, any slice of this object you take, it's circular in nature, and it's like the same from all the sides. That's what is a sphere, and it's a 3D object, and that's what it separates from a 2D object, which is a circle. Okay. So now the beauty is, since we have been learning different topics of mensuration, we started from cube, then cuboid, and then we came into cylinder. And the moment we came into cylinder, I discussed that once you understand cylinder, which is the most easiest part, all other subsequent 3D objects which we have covered, including today, that is sphere and cones and all other things, frustum of a cone, everything can be easily imagined or derived if you understand the concept of cylinder, because all these 3D objects, whether it's cylinder or cone or sphere or a hemisphere, are kind of related in unique ways. And interestingly enough, Archimedes kind of discovered that, and he had another eureka moment when he was trying to compute the volume of the sphere, and then how he related the sphere and cylinder are kind of related, and we can calculate from that. And the same concept, if you think from an exam standpoint of view, if you just remember cylinder, there will not be any need for you to memorize any of the formulas, because over a period of time, when you put all the shapes 2D and 3D together as a part of the syllabus for any exam, the number of formulas kind of add up, and it's very confusing, and you can make a mistake. So instead of kind of memorizing it, what you can do is you can just remember the formula for cylinder, and subsequently you can derive everything on the fly, saying that okay, this is what it is. And this episode is going to just talk about those kind of tips and tricks. How should you remember the formula, and also kind of help you with the examination problems. So let's talk about this in the context of sphere. So like I said, these 3D objects like cone, sphere, over here we have the cone here, let me mark it here. Okay, we have the cone here, we have the sphere here, and we have the cylinder, and then we have the hemisphere here, or you can take it here. Hemisphere is nothing but two halves, or two half hemispheres, or two hemispheres make up a sphere. So when you cut the sphere exactly into half, like a coconut, half coconut, right? That's what hemisphere is. So all these shapes are related. And the trick to understand the correlation or the relation while deriving the formula is just imagine for a second that all these shapes, whether you take a cone or a sphere or a cylinder, what you need to imagine is the height. If you see this cone, the height of this cone from this point to this point is same as the height of the sphere, and is same as the height of the cylinder. If you see this particular mark over here, that kind of this rectangle over here, this kind of captures that. If you assume for a minute that we have three 3D shapes, namely cone, sphere, and cylinder, and if you assume that all of them have the same height, which is what it is over here, and all of them have the same radius, whatever is the radius, or the diameter, whichever you want to take. This is the radius part, or you can take the whole piece of a diameter, and this is the diameter. So the radius and the diameter also is the same. If you think from that standpoint, it's very easy to derive the formulas for a sphere in this context. And let's talk about that, okay, how it is, okay. And if you see here, one of the tricks is, let me get rid of this 1 second. If you see here, one of the trick is for the sphere, the height of the cylinder or a height of the cone is nothing but it's still a diameter for the sphere. So in this case, the height of, although we say all of them have the same height, the height in the context of sphere means it's a diameter. However you see it. You see it this way or you see it this way. The height of cylinder and cone matches or is equal to the diameter of the sphere, because the diameter of sphere, however you cross-sect it, is going to be the same. That's the beauty of sphere. So you have to just remember that nuance, that height of all the objects are same. Height is nothing but the same as diameter of the sphere, and each shape has the same radius or diameter over here. If you see this one, if you see this one, and if you see this one. So if you just remember that nuance, it'll make the context very easy. Now there are two ways that you can remember that, and it's up to you. I'm going to just present both the ways. You pick up whichever is easy for you to just remember. First, we'll talk about sphere or remembering sphere in terms of cone, which talks about the relationship between a sphere and a cone. Okay. So what does it mean? And if you take this YouTube video, I put a video over here. You can take this, but I'm going to just explain it. If you want to play it offline, you can play it. What it tells is, if you take a cone, since we're talking about the relationship between a sphere and cone, if you're trying to fill water in a cone or in a sphere, let's say you take a sphere like this, the green one, if you see here, okay, and you're trying to fill this completely with water. So how many cones you will need? This is a cone here. So how many kind of cones you will need, or how many times you have to fill up this cone to fill up this sphere completely to the full? And interestingly, if you see this video, it takes 2 cones. That means you have to take 2 cones of this size, okay? And the assumption is that we said here, the height and the radius and the diameter are going to be the same. So if you take that dimension, it will take 2 whole cones. It will take 2 whole cones to fill the sphere completely with the water, okay? So what does it mean? It means that if you take this cone here, green and blue here, if you fill up the green one with water and pour it into a sphere, it will fill half of it. Then you take the blue one and then again you pour into a cone, and there's a blue part. So it takes 2 cones to fill up the complete water. And like I mentioned, to reiterate, the assumption is we are going to assume 2 cones and a sphere, 2 cones and a sphere. Let me scroll down, where the radius and the diameter, radius or diameter, you can use it interchangeably, are the same across all the shapes. The radius or the diameter of the cone here is same. In addition to the height of the cone, this height of the cone is nothing but, in the context of sphere, it's still, if you call it as a height, for a sphere it's still a diameter. So just remember that. The same thing I'm trying to explain from this figure, I'm talking about the same thing, okay? So if you explain that, then we'll see how do we use this geometric assumption that we're talking about, and the whole notion of we require 2 cones to fill up the water in a sphere, which means the volume of one sphere over here is going to be equal to 2 cones. That's what we're trying to talk here. So the volume of one sphere is equal to 2 cones. That's what we're going to talk. And that's what I have written here. So volume of a sphere is equal to volume of 2 cones, because that's where the water completely matches. That's what we can say in other words. In other words, volume of a sphere is twice the volume of a single cone. And we already know the volume of a cone, which we derived in the section when we explained cone, which itself we derived that a cone, we require 3 cones to fill up a cylinder, and that way we remembered that cone in terms of cylinder, we got this formula that volume of a cone is 1/3 pi r square h. This pi r square h is nothing but a volume of a cylinder, and we require 3 cones to fill up a cylinder, and that's where you get this 1/3. So in that sense, we derived cone in terms of cylinder, and now we are trying to derive sphere in terms of a cone. Okay, so what does it mean? Volume of a sphere is twice the volume of a cone, and hence we get this substitution, twice the volume of a cone in the bracket 1/3 pi r square h. But we know that the height over here is nothing but the diameter of the sphere, which is what the assumption that we have made, and we can substitute the height by the diameter over here like this. Okay, sorry about that, let me erase that over here. And the diameter itself is nothing but twice the radius. We know that. That's the simple. We always know the diameter is twice the radius. So what we're going to do is we're going to substitute this part over here. So let me come again from the top. We are going to substitute the height with the diameter, because we are assuming the height and the diameter are the same for this figure. And then since we know from plain a circular form or circular object, the diameter is always twice the radius. So we're going to substitute the diameter with 2r, and the rest is just simple manipulation. So we have over here at this point in time, volume of the sphere is equal to 2/3 pi r square, which is coming from here, and the d we have substituted as 2r. So we have got r square here, we have got r. So if you say we have got r square here, we have got r. This 2, we are moving it outside over here, if you see. So after manipulation, we get the equation as volume of a sphere is equal to 2 by 3, then this 2 into the brackets pi r square into r, and this r square and this r when multiplied becomes r cube, and this 2 and this 2 when multiplied it becomes 4, and hence we have the final equation. Volume of a sphere is given by 4 by 3 pi r cube and cubic units, because it's a volume, don't forget that it's cubic units, whatever is the units, whether it's meter, centimeter, whatever it is, you can get that. So that's how we can remember or we can derive. So if you just want to memorize this, it's okay, but if you're struggling, don't worry about that. Just remember it takes 2 cones to fill up a sphere, and quickly put this formula and you can easily substitute that and you will get this formula. Volume of a sphere is equal to 4 by 3 pi r cube units. In the similar way, I'm not going to explain in detail. In a similar way, if you want, you can also remember the formula for sphere in terms of cylinder. Normally, I use cylinder as a benchmark for everything. It's very easy so that you don't have to get confused. So on a similar example, if I fill up the sphere completely with water, okay, and if I try to pour the water into a cylinder, how much portion of the cylinder it fills? It's a similar exercise to what we did in a cone. So we know that to fill out the cylinder completely, we require 3 cones. In terms of sphere, if the sphere is completely filled with water, I'm just going to pour it down into a cylinder, it kind of roughly fills, not roughly fills, it fills 2/3 of the cylinder, okay? It doesn't fill it completely, but it fills 2/3 of the cylinder. So this is a 1/3 and this is a 1/3. If you add that, it's a 2/3, okay? So if you see here, I put it here, a sphere fills 2/3 of a cylinder. So what does that mean? I'm taking the sphere, pouring the water, and if you see, it's almost 2/3 or 2/3 is filled out and 1/3 is left off, okay? That's what it is. And the same assumption we are going to make over here. If you see, I've inscribed the sphere inside a cylinder, and this is where Archimedes was kind of a genius, and this is how he kind of figured out the formula, how to figure this. I'll try to put out a separate episode if you just want some entertainment of what Archimedes was trying to do and how did he come with another eureka moment in his life. But nevertheless, if you think about a sphere inscribed within a cylinder, that means a sphere is fit inside a cylinder which is in the dotted line. So what it means is this is going to be the diameter of the sphere, and incidentally this is also going to be the diameter of the cylinder with the circular bottom over here and over here. And the same diameter, when you vertically flip it, it also becomes, for the cylinder it becomes the height, but for the sphere it becomes the diameter. The same assumption that we took over here, nothing different. Over here, if you see, the same difference we took over here, right? And that's what they are putting it over here also. If you see here, the height is equal to 2r because the height is equal to the diameter, which is equal to 2r, and the r is coming from here, okay? And we know that once we pour down all the water from a sphere, it fills 2/3 of a cylinder, okay? So if we apply that formula over here, see, this is showing us 2/3 of the water, okay? And over here you will see all the dimensions. This r is the radius of the circular top in the blue for the cylinder, and the same is the radius for the sphere also. And the height of the cylinder is nothing but 2r, which is what the diameter of the sphere is. Hope that's not confusing, okay? That's what we're talking about. Height is equal to 2r is equal to diameter. With this notion, like we had on the left side for the cone, we can also derive the formula for a volume of a cylinder if you kind of relate it with the combination of sphere and cylinder. So what is the volume of a sphere? Volume of a sphere is nothing but 2/3 volume of a cylinder, because that's what we get here. When we pour down the water, it fills 2/3 of a cylinder, okay? That's what we get it here. And we already know the volume of a cylinder, which is nothing but pi r square h. And again, if you substitute h of a cylinder is nothing but diameter of the sphere. That's what we kind of concluded here, or that's what we kind of made an assumption here, okay? And again, the same thing like I explained on the left side over here, the diameter you substitute with 2r, and when you make the manipulation, you still end up getting the same equation where you kind of conclude that the volume of a sphere is equal to 4 by 3 pi r cube cubic units. That's how you derive. So I gave both the explanation just to give you a sense that you can remember however you want. Both of them are not necessary. If you don't want to mug up the formula, just keep it in mind that I'm going to derive the sphere in terms of a cone or in terms of cylinder, whatever you want. If it's cone, it's going to take 2 cones to fill a sphere. If it's going to be cylinder, a sphere is going to fill 2/3 of a cylinder, and that's how you kind of remember it. Okay, and so once you derive the formula for a sphere, hemisphere is going to be easy, because hemisphere is nothing but when we get a sphere split into half. So we have two hemispheres, 1 and 2, sorry about that. So 2 hemispheres make up a sphere. So since we already know the formula for a sphere, if we exactly divide this formula by 2, make it into half, we will get a volume of a hemisphere, and that's what we're going to do here. So volume of a hemisphere is equal to 1/2 of volume of a whole sphere, based on this diagram over here, right? And what we get, volume of a hemisphere is equal to 1/2 into volume of a whole sphere, which is nothing but 4/3 pi r cube. And when we cancel out this and this, what we get is volume of a hemisphere is equal to 2/3 pi r cube cubic units. Okay, it's simple. So again, you don't have to mug up. If you know the volume of a sphere, then you can just divide it by 2 and get the volume of a hemisphere. So that way, no need to memorize any formula for mensuration except for the cylinder, which also is easy, and then from there you can derive it. Okay, so in closing comments, what are we trying to say? Any 3D objects that we discuss here, sphere, cone, hemisphere, anything that you're talking about, think about that object in the relation with some reference object, which could be cylinder or a cone. So I've computed both for you, so you can pick up any one of this that helps you remember either a cylinder or a cone. And cylinder formula is easy because you already done that, and then everything flows from there. Okay, and in summary, volume of a sphere is equal to 4/3 pi r cube cubic units. The cubic units is in red so that you don't forget. And volume of a hemisphere is, you just divide this by 2 and you get this equation. So that's how we learn how to compute the volume of a sphere in the context of mensuration. And then we'll talk about some examination problems and how to remember this. Hopefully this was useful. I'll see you with the next topic.